One more example of a greedy algorithm here is the conversion of a decimal number into binary number. If you recall correctly, how do we actually convert a decimal number to binary is essentially like if we have a number, let's say like 55, what we would do is we would divide this number by 2 and use the remainder of that number, and we keep on dividing till that approaches 0, and whatever are all the remainders, we just write the remainders bottom up, which is in this case, let's say if we want to convert 55 to binary, what we would do is we would divide 55 by 2 to get 27, the remainder will be 1, again divide it 13, remainder will be 1, again divide it 6, remainder will be 1, then again divide it, we get a remainder 0, the value 3, again divide it to get 1 and a remainder of 1, and finally we'll get a remainder of the divisor will be 0, and the value here, the remainder will be essentially 1. So the binary conversion of 55 would be something like 110111. And typically we saw a few examples on how to do this using a stacked data structure where you repeatedly take the mod of that number. So that was essentially a brute force approach of solving the same problem. You can use a stack to compute this. There are a lot of other ways to do it. Like how you do it using a greedy paradigm is you start with the largest power of 2 that will actually fit that number, and how you can determine this large value of power of 2 is you can essentially check, like basically like if you have a number, you can determine like or pre-compute the powers of 2 and store them like in a map or in an array, which is you would have like this, which is 1 2 4 8 16 and so on, like a really large array consisting of these different powers of 2. And what you essentially do is you find out the correct number which where the number is just slightly smaller than the power of 2, so it should not be so essentially how you compute that is you go to the next number which is the larger than the current number, which is in this case, like let's say if it is 280, there will be two numbers, 256 and 512, and 280 lies in between these two. And in this case for 280, what we would do is we are more interested in 2 to the power 8, which is this number 256. And what we do is we know, like if at the index 8 in this array we would actually have this number 256 and so on. So because we are storing a number here that represent an index which is 0 1 2 3, like these are array indices, and the value corresponding here in that particular index is essentially 2 to the power that index and so on. So essentially you can use these indices, and this would represent the 9th significant digit in our number. So you can keep a track of this, which is in this case the 9th significant digit, because we had at index 8 this number 256. What we can do is we can utilize that. We would know that at the 8th index that would be the largest index, and that would be storing a value 1, which is sorry at the 9th index it would be storing a value 1. Next what we do is we reduce these two numbers, which is we deduct 256 from 280. We find that the remaining number that we have is 24. We again do the same approach, which is in this case 2 to the power 4, which is 16, is the closest one because the next one would be 32. And we know from this particular index that the index plus 1, which is the 5th index, would actually be 1 in our binary number. Next we repeat that, which is we deduct 16 from 24 to get 8. And we know that 2 to the power 3 is 8, which is the closest integer that is close to 8. So essentially, like since this is the 3rd index, we just do index plus 1, and that would actually also store 1. Other than that, all the numbers would be actually 0. So this algorithm, like you can actually store all of these numbers in a form of an array, or what you can do is you can just generate them on the fly. So either one of them is fine. But the key idea here is that, like, for very large numbers, like for small numbers, it won't make a difference even if you use stack. But for very large numbers, this algorithm would be a little bit more faster compared to your brute force algorithm. So with that, what we are going to do is we are going to start discussing the last problem for the greedy algorithmic paradigm, which is the Huffman tree problem. And I think I'm going to introduce you to that problem in the next lecture. Thanks.